2017. Then he worked as a postdoctoral fellow for a year at Department of Mechanical and Aerospace Engineering in Syracuse University, New York. He also worked as a postdoctoral fellow in Department of Aerospace Engineering in IIC. Then he currently he is an assistant professor with Department of Electrical Electronics and Instrumentation Engineering in BITS Pilani, Goa. So his research interest lies broadly in the area of systems and control. In particular, some few fields are nonlinear control, multi-agent system formation control, geometric control, etc. So we, from our behalf, would really appreciate that Dr. Rakesh agreed for this talk in our platform, and he will talk about finite time control and estimation. So Dr. Rakesh, you may go ahead with your presentation.
Thank you, Siddharth.
Yeah.
Let me present this one. So let me know if you are able to see it as full screen or short one. Are you seeing full screen?
It's visible, but not yet full screen.
Okay. Let me just do that. Okay. Is it full screen now?
Fine.
Okay.
Yeah, fine.
So I won't be able to read any comments. So if somebody has any issues while listening or anything else, Siddharth, you can let me know.
Yeah, I'll let you know. Yeah.
Okay. So talk would be very short. I mean, not for 1 hour for sure. Probably 1/3 of that. So what I plan to cover is essentially finite time control and design, and actually the estimation part. But the estimation part would take significantly more time for me to explain. So I am not going deep into the estimation part. I'm only outlining the results regarding the estimation, which are actually more recent. But so without further ado, I want to thank organizers for inviting me here. It's good to get a chance to talk to PhD students from SysCon. So let me start. So I want to start from a simple old paradox. So most of you might be familiar with the idea of Xenos Paradox. So Zeno was a mathematician and a thinker, more likely a philosopher, who lived in the ancient Greece. So he came up with many paradoxes. So one of the paradox was race between Achilles, who is a very quick runner, and a tortoise. So he starts with saying that if Achilles starts 10 meters behind the tortoise, and Achilles runs 10 times faster than the tortoise, his paradox implies that Achilles will never catch up. So why does he say that? He says that, so for 1 minute, suppose Achilles catches up the 10-meter distance, then tortoise would have already moved 1 meter. And if Achilles moves and catches up that 1 meter, then tortoise would have been going 10 centimeters ahead, and etc. and etc. So as he moves, always according to this idea is that always Achilles is behind tortoise by some value. And as we know, this is a paradox is easily resolved if you know that if you have an infinite series of values whose geometric series with a proportional coefficient less than 1, then the summation is a finite. So if you have 1 by 10, in this case 1 by 10 plus 1 by 100 plus 1 by 1000, etc., it will sum up to be just a finite value. It is not infinite, and because of that, Achilles would easily catch up and overtake, as we know in the real world. Okay, why did I give this example? I'm actually trying to explain what is the issue with asymptotic stability. So the asymptotic stability is somewhat similar, except that you have a system, you want to take it to origin, but your velocity by which, or the rate at which you go to origin, if you have asymptotic system or a linear system, then that is actually decreasing. Okay, let's go to the actual math and then see what is happening. consider a simple case where x dot equal to minus alpha x. This is a simple linear system, and again, I'm not even assuming that this is scalar. It could be a vector. That is fine. Only thing what I want to know is that what will happen to the origin. And we know that the origin is the equilibrium point, and system will finally be exponentially converging to origin, because the solution is known to us, and the solution is exponentially converging e raised to minus alpha t x of 0, x0. However, as you can see, at any time for going from, suppose x is equal to certain value to its half of it, suppose it's a scalar value. Suppose I want to take the half-life. The half-life is always same. So suppose I have a scalar system, and if I had the x to be a scalar, then from x0 to half x0 will always take log 2 by alpha, which is very related to the time constant. I'm not going deeper into that, but this is like a half-life. And this means that every time you want to get closer and closer to origin, but you will never reach origin. You will never reach origin because the time to take from 0.1 to 0.05 is same as taking from 50 to 25. And since this is not, so why I want to give this example was, unlike the Achilles example, your runner, in this case your system, is actually decreasing the speed as you get closer and closer to the goal. And because of it, you actually never reach infinite time. So this is a case where you have asymptotic stability, and this is what I gave as a simple example, exponential stable linear system. But this example is valid even in the case of a nonlinear system. Either it is, if it satisfies exponential stability or asymptotic stability, then you have the same problem. Actually, this is more deeper than that. We'll come back to that. But why do we need a finite time stability? Okay, some of you might ask, suppose I'm giving you that, okay, I cannot specify a particular time at which it will exactly be 0, but any finite bound I give around the origin or around the equilibrium point, I can always reach infinite time. For example, consider what happens in the physical world. So you may think about a radioactive material. A radioactive material has an exponential decay, and we can even work out similar equation there. And additionally, we can think that as the half-life is something that is extremely valid there, that is something commonly used there. So what do you mean by having an infinite time? The infinite time does not work out there because atoms are discrete quantities. So finally, if there is only one atom remaining of the radioactive material, then that radioactive decay will eliminate that material. So there are radioactive materials which are very, very short half-lives, and they end up completely destroying themselves. They completely decay, and none of the atoms exist in the universe anymore. So that can happen. So, but then question is, why do you need finite time stability? Why do you care? So the problem comes from two analytical aspects. Now, again, I cannot say that these things cannot be solved any other way. That is not my claim. But these problems I have faced when I tried to research, and these are problems that is commonly seen in many of the literature. So one example is having like a two-loop system. So like I have an inner loop and I have an outer loop. So for example, think about a simple case where you have a drone is being controlled. You have a target signal position, and you have a position controller which is acting as an outer loop, and you have an attitude controller. And this outer loop and inner loop are important because the drone, they are coupled. So you are in the case of a multi-copter, you have the dynamics such a way that your rotation, your attitude is the one that determines how the position control is applied. Now, again, I'm not going deeper into the dynamics there, but general idea here remains that if I have an asymptotically stable attitude controller, then I cannot say that my position will also converge in a certain time, because my attitude itself is taking asymptotically infinite time to converge. So what often happens is that you will be able to say that overall system is convergent, not even asymptotically stable. And this often happens in many analysis cases. And I am not saying that that is finite time stability is the only way to avoid this. However, finite time stable, if I have inner loop to be finite time stable, then that is definitely helps me, because after t greater than a certain capital T, I can say that my attitude has converged. So my desired attitude is met. And after that, my position can take, and even my position is finite time stable, my overall system will be asymptotically, sorry. If my position controller is just asymptotically stable, I can still get that my overall system is asymptotically stable. So that requires to have some kind of finite time control property, finite time stable property for my inner loop. This is a very common problem that you would encounter in many practical applications. So the problem, yeah, you can say that this is a theoretical artifact, but when you theoretically prove it, you want to get more stronger stability condition. Similar problem comes up when you have an estimation algorithm running. Suppose you have an estimation algorithm which is estimating either attitude or position or some other parameter of either a drone or a robot. Now, if your estimation algorithm is again asymptotically converging and your controller is also asymptotic, then you need some way of separating them two. So you can either say that your combined dynamics you need to prove, or you have to prove that there is a reasonable separation principle active there. Without which, again, theoretically, you cannot say that, okay, you are trying to estimate something, that estimation is not converged, but you are still able to work out and use that parameter estimation value for your control. An additional aspect is that when you have finite time convergence, you actually finite time stable systems, you actually get a better rejection of disturbances. This we can see at least a bit of that in later examples. So these are some of the motivating reasons why we want to go with finite time stable control laws. Now, finite time stable control laws can be done in many ways. So one of the easiest or one of the mathematically easy way to look at is to have a discontinuous control scheme. For example, if I have x dot equal to signum of x, then I can actually say that, okay, I will be able to get finite time stability, because unlike the last case, in this case, if I am having similar case of a runner, that velocity does not decrease below a certain value. So the velocity at worst becomes -1, or in this case +1. So signum is essentially the sign of the value x. That can also be done as term-wise for vector. So this idea is useful, and this idea can be explored further. Of course, many of the switching controllers, many of the sliding mode controllers rely on something similar. Of course, not exactly something as crude as the signum, but having something more elaborate and more detailed than that. However, the basic idea remains that you are still having a discontinuous control scheme, and many of the cases, of course, higher order sliding mode control can avoid it, but other cases, this can lead to chattering. And chattering is in many ways dangerous for a practical control system, as it can introduce high frequency and go to unmodeled dynamics. Additionally, you can have actuators which does not support providing discontinuous controls. So one example is again attitude control. So if suppose you have an orientation control of a rigid body, then you don't really have a discontinuous control. You may not have a discontinuous control option at all. So in this case, what we are trying to look at is finite time control schemes which are continuous. Now, continuous is actually, you need to have an asterisk there, because you cannot have Lipschitz continuity. Okay, why do we cannot, or why we cannot use Lipschitz continuous systems? So one advantage or one reason why you look at the Lipschitz continuity is that we actually get uniqueness of solutions. In fact, if you have a system which is Lipschitz continuity in state and piecewise continuity in time, then you are getting both forward and backward continuity, or both forward and backward uniqueness of the solution. So here there is a problem. Suppose if you have a system where your trajectory is converging in finite time to an equilibrium point, that means that if you go backward from that equilibrium point, like the tenet thing, if you try to go back from the equilibrium point, you have multiple possible solutions. You can either remain at the equilibrium point, you can start at a particular initial condition, or you can start from a number of initial conditions. So which means that finite time convergence violates backward uniqueness. This is not necessary for us, but that means that system cannot be Lipschitz continuous. So we essentially try to synthesize Holder continuous schemes, which is a much, I would say, less stricter than Lipschitz continuity. And we try to have Holder continuous systems, which would be having a forward uniqueness. So the solutions would be unique in forward time, and we are trying to construct such control schemes. So we want to construct continuous finite time stable control schemes, but since we cannot have a Lipschitz continuity, we are going for Holder continuity. And since we cannot have uniqueness in backward time, we are focusing on uniqueness in the forward time. Okay. So far, do you have any questions?
I think it's fine, sir. You can go ahead.
Okay. So I'm going to some of the classical theorems, which essentially outline how we can have a Lyapunov function that would specify to have the finite time stable systems. So this actually one of the earliest works regarding this was done by Professor Sanjay Bhatt and Professor Dennis Bernstein in their finite time stability and continuous autonomous systems. Actually, they have multiple papers which was almost simultaneous around the time, and they have outlined especially the autonomous systems. This particular theorem which I am referring to is from the second paper, that is from Professor Wasim Haddad and his collaborators, which essentially look at time varying systems as well. So again, I don't want you to go through everything and get lost here. But the basic idea here is that you want to construct a Lyapunov function V such that V dot is less than or equal to K into V raised to some lambda. And that lambda is a fractional value which is less between 0 and 1. And that is the crux of what we are trying to do. So we are trying to essentially construct a Lyapunov function such that we will be able to get a Lyapunov derivative of the Lyapunov function V dot, which would be less than minus into some proportional quantity. Of course, we want it to be negative, and raised to some value lambda. And that lambda is fractional. And if the lambda was not there, if it was just V dot less than or equal to minus KV, we know that that would have given exponential stability. Here, this is a finite time stability requires that you need that lambda, which will be a fractional power. And the entire idea of the talk and essentially the control design for the finite time is to go to construct such a Lyapunov function, which is essentially a control Lyapunov function, and from there tries to glean what kind of control law would enable us to get this condition. Okay. So let's look at a simple second order system. This is more an example which is trying to explain to you how this is done. And again, I'm not going further deep into other examples, but so we will see this basic idea here. Suppose you have a system. This example is from one of my papers. So the basic idea is that you have a simple second order mechanical system. This B and B are actually vectors. So B is a position, V is a velocity, and you have this GE3. So according to the standard convention, GE3 is essentially the gravity, which is shown to be acting upwards, and the control is acting downwards. That is a convention of the direction. So typically for the drones, that is how you determine. So finally, you have the desired trajectory, which you need to follow. You know the VD and BD values, you want to follow them. And you can, as always, you can construct the error variables, which will be just obtained by taking the difference between them from the actual and the desired. And we can obtain the error dynamics to be of the simple form. So nothing too fancy here, very basic derivation. Once we have this idea, once we have this error dynamics, we can then go ahead and construct a Lyapunov function. So before we go to the Lyapunov function, we construct some value called Z. This Z is actually specifically constructed such that this is not, you can immediately see that this is essentially constructed such a way that you have when the Z of t as B hat goes closer and closer to 0, Z of t doesn't go immediately as fast to 0. It's actually, it will be much slower than that. So that is the essential idea by which we want to construct our control, because we know what is the issue. If we have asymptotic control or asymptotically stable control law, your B hat or your feedback value, the value that you are feeding back, will go closer and closer to 0 as you are getting closer and closer to 0. That is a problem. So we don't want that, and essentially we don't want a discontinuous as well. So we are essentially constructing a continuous parameter Z, not exactly parameter, dummy variable Z, which we are ensuring that it will not go as quickly to 0 as B tilde is going closer to origin. So this is essential idea. And then we are essentially constructing a Lyapunov function of this particular form. Now, if you have used control Lyapunov design before, you can immediately see that this design is a Ortega construction. So Ortega construction essentially means that you have the first term, in this case B hat transpose B hat, and the second term is typically the V plus B hat. So in the standard Ortega construction would be employing V hat plus K into B hat transpose or C dot or the dot V hat plus K into B hat. So that is how we typically design the Ortega construction, the Lyapunov function with the Ortega construction, and which would often give you a V dot to be less than or equal to some value into V. That is what we try to obtain in many cases. That is how we go with designing controller. Here we are, instead of B hat, we have the Z time, and the Z term will be able to provide us with a, as we already saw that this term will be crucial for our control design. So let me go ahead from this. So since we have the Lyapunov function, now what we need to do is that we are going with what is the derivative. So, and we will see what kind of control law U would enable us to get the condition before. So we want to get VTR dot to be less than or equal to some value K into VTR raised to some fraction. So here the steps are outlined here. We can see what is happening. This is basically the standard differentiation, nothing too fancy here. But immediately what you get here, can you see my arrow?
Yes, yeah.
Okay, so you can see here what is the terms that is obtained. You have the GE3, U and VD dot minus KZ, plus KZ. So this plus KZ dot is we need to cancel out. You need to cancel out this GE3, you need to cancel out the VD dot, and rest you need to be chosen such a way that you are getting a positive definite term that is coming from here, and you need to cancel out this term. And that is what we are choosing here. If you see here, this term essentially ensures that the terms are getting cancelled out, and we are getting a term which is in terms of K into B tilde transpose KZ, and you have another term which is this complicated term with Kp, and if you see above and below, you will immediately see that they are same except this 1 minus 1 by p term is coming there. So this all structure is chosen such a way that we are able to obtain terms like this, k into b transpose, so b tilde transpose b tilde raised to 1 by p. Similarly, this particular term raised to 1 by p. And these are essentially made sure so that we can get something similar to the Lyapunov function we started from. So this we are getting, this we are getting. Now only thing we need to make sure is that, but actual Lyapunov function we wanted. So if you look at here, quickly we can see that the Lyapunov function instead has the sum here, and here the 1 by p is inside. 1 by p is the right kind of fraction because p is chosen to be between 1 and 2. So 1 by p is less than 1. So that is satisfied, but only thing is that p is inside, so we want the entire thing to be outside. Now we will use a lemma for that, and which would enable us to claim that finite time stability is satisfied. So, okay, let me go here. If you see the particular lemma, again, this lemma is very commonly used in, again, finite time literature, especially finite time continuous control laws. This is nothing that complicated because we are essentially using that these are concave functions, and we can get this inequality. So we have p greater than 1 and ab is to be positive numbers, then a raised to 1 by b plus b raised to 1 by p is greater than or equal to a plus b raised to 1 by p, which would mean that I can take 1 by p outside of these two terms, which again, as we have already looked at, would give us that v transpose derivative is less than or equal to minus k v transpose raised to 1 by p. And this is what we needed from Professor Butt's paper and Professor Haddad's paper. We wanted these to satisfy so that we can get the finite time stability. Now, okay, once again, if you want to ask anything in the middle, you can. Do you have any questions? Okay. So this result is from the paper mentioned here. The basic idea is just to construct a control law so that we are able to get a finite time stability of the translational feedback control. So this particular case was actually this particular paper we are looking at a control of a UAV where both the position control and the attribute control are constructed such a way that both are finite time stable, and that is made to give overall finite time stable control scheme. So here, okay, I just want to go back 1 second here. Now, if you look at this particular dynamics, this particular equations, so one of the things I wanted to highlight is that suppose I have a disturbance. Suppose I have a disturbance with respect to the control law. Suppose I had an extra term coming to the control law, which is creating a constant noise or a persistent disturbance. Suppose that is happening, then I can take that term out, and then I can say that what is the maximum value of that value, that noise, for which system would be having v dot to be less than, or sorry, v dot greater than 0. So this is often done for the robustness analysis of a Lyapunov based control. So what I wanted to outline is that compared to an asymptotic control law, because of the terms associated here, essentially because of this raised to 1 by p term coming here, you actually have more robust control law because additional disturbance that is needed, the same amount of disturbance constructed here would do less trouble compared to an asymptotic control scheme, because the same Lyapunov function we can use. So similar Lyapunov function we can use for the asymptotic control law as well. Only thing is that we will use instead of z, we will use b hat. So that can be used. That's why I just want to compare those two. Okay. So most of the major thing that I wanted to explain is already done. I will just go through some basic ideas regarding the attitude estimation and attitude control, and I'm not going deeper there. Okay. So, however, when you actually construct the problem in SO3, that is the manifold in which attitude is represented. If you have a rigid body dynamics and you have the attitude represented in SO3, then continuous finite time control is a bit more tricky there, because there are the presence of additional equilibria. So which is unavoidable. If you have a continuous control law in SO3, then it will definitely have additional equilibria. So it will actually have 4 equilibria. So you cannot have finite time stability or global finite time stability. The best you can have is asymptotic or almost globally finite time stable, which essentially means that you are having a one equilibrium which is stable and which is finite time stable. Other equilibrium points are unstable, and the region of attractions of all the other equilibrium points which are not stable, which are not desired, end up being of zero measure. But the zero measure part is a bit tricky aspect to show. However, the basic idea remains that you are practically ensuring that your system will converge to the almost globally finite time stable equilibrium and not to the unstable equilibrium that may be present. So this is essentially one tricky part compared to SO3. I'm not going to the design in SO3 or the estimation part, because that requires some more explanation which I didn't know whether to be I could complete. So here I'm trying to conclude the basic ideas what I covered so far. So we looked at why we need finite time stability and how we can design finite time stable controllers, and some basic, some further reading you can do in these works here. So these two papers, the finite time stable attitude estimation and finite time stable attitude and angular velocity bias estimation, actually provide some results regarding recent results regarding how we can estimate the attitude with some vector measurements and what are the challenges there. And also the second paper actually shows you in the case of a finite time bias estimation. So that is actually having some more works there. So let me conclude with this, and if you have any additional questions or remarks, please go ahead.
Yes, so there are few questions.
Yes.
One is, can we evaluate the time of convergence? How is it different from fixed time stability?
Okay. So fixed time stability essentially implies that if you have a system which is fixed time stable, then you have an upper bound. So you have a capital T which is an upper bound. So from any initial conditions, you can only take this much time to converge to the equilibrium point. That is fixed time stability. Fixed time stability in places like SO3 is not that complicated, because you will always have an upper bound regarding that, because the manifold itself is not very infinite. So again, I cannot say that it's not infinite, but yes. So the idea is that it is comparatively smaller manifold where you are working with. But in general, finite time stability means it will converge in finite time, capital T, but there is no upper bound in finite time stability. I think some of the very, very old papers, they use fixed time stability as way to describe finite time stability, but nowadays it is two different concepts. So finite time stability means that there is a capital T after which you are able to converge or you are stable, and fixed time stability means that there is an upper bound on that capital T. Yeah.
Okay. There is another question by Dr. Gayatri Kundu. So she is asking that design of suitable Lyapunov function plays a key role to apply Bernstein's theorem. and she was wondering if you could tell us a bit about how difficult this design of such functions in general.
Okay,
Maybe if you
so
have tried it for some cases, you could
yeah,
explain.
so okay, yes, it is tricky. I mean, I actually don't have any. I don't know if anybody has a universal way of doing this. But in the case of a general Euclidean space, you have some ways of getting there. So actually, there was one paper which I didn't include here. There is actually from Jorge Cortes. So he explains about how we can construct if you have a gradient vector flow, and that gradient vector flow is already ensuring that you have asymptotic stability. Then how you can modify it so that you will be able to obtain finite time stability. That is something that is discussed by Cortes. But yeah, that does not mean that it is always easy, because in many cases, especially if you have a manifold, you have much more tricky way problems, because you cannot violate some certain aspects. And I would say that in the case of a Euclidean space, this is pretty much taken care of to a certain level. But yeah, the controllers may not be always easy to implement. You are probably canceling out so lot of non-linearities and then implementing it. So yeah, I'm not saying that they are all very usable, but that can be constructed in the case of Euclidean space. In the case of a general manifold, I am yet to see any work which solves it for a general case. Atrey, does that answer your question?
I think she's having some mic problem, so.
Okay. Okay.
So
Yeah,
I have
but yes, continue.
Yeah, so I have a naive question that, so whenever you are doing control in SO3, that is the special orthogonal group, so those matrix Lie groups are actually, I mean, if I think them as some subspaces of R9, that is 9-dimensional Euclidean space. And so now SO3 have some certain properties. So I can also translate those properties to this 9-dimensional vector space. So how different doing control in that manifold, and I mean, is there any good equivalence between those two spaces? That is, are we losing too much generality if we convert the control problem from manifold to Rn?
So there is two things. One is that you may have a continuous curve that is happening in your general matrices, but that may not be the case when you convert back to SO3. In SO3, that may not be a continuous curve, because if you just use projection, that is often a problem. Additional aspect is that you're essentially, so there are two major aspects. One is that you may end up, so basic ideas regarding the singularity, that is when you represent a rotation matrix by some other, so when you represent attitude by some other methods, result essentially because of what you are losing the important aspects regarding it. You are losing the inherent parts regarding it. Even when you are actually simulating something, so suppose you are numerically integrating and you are not using an integration techniques which respects the Lie group structure. So for example, ODE45 doesn't entirely respect it. So it can create problems where you are actually getting an attitude which is not actually attitude. But yeah, that won't be noticeable if you are looking at a very small time frame and not very large number of agents. That won't be a major issue. So additionally, I would say that looking at rotation matrices probably makes it easier in some aspects, because you are actually not looking everywhere and you are actually not trying to control everything. You are probably would do better job regarding that if you respect the geometry, and that is, again, that is just my feeling. I don't think that that is necessarily required.
Yeah. Okay. Yeah. Does anybody has any other questions? Okay, I think no more questions. So
Okay.
thank you, Dr. Rakesh, for this talk. We really appreciate that giving this talk in this kind of time. I mean, it is a vacational time, so yeah,
Yes.
thank you. And okay, so we
Okay.
will call it a
Yes.
day then. Yeah,
Yes.
thank you.
Thanks, Siddharth. Thanks, Harsha, for inviting me. So, yeah.
Okay, yeah,
Okay.
thank you.
And someone has asked the question about recording that we have on our website called SysConTalks. You can Google it, and I will send it. I will put it the link of the
I,
website here.
yeah, yeah. I think in the mail, the website link is there.
Yeah.
Mail.
So where I have mailed it is there.
All right. Yeah.
Thank you.